Have you ever stopped and thought about your shoes? The traditional way of making a pair of shoes presents many problems for the manufacturer. For instance, a special cutting blade is needed for every individual design, every section, indeed every size of shoe. They have to be positioned by hand and a press used to stamp out the shoe components from sheets of material. Another major problem is waste. The machine cuts by compression, so that the operator must leave a gap between the cuts. An experienced operator makes the best use of a sheet of material, but there's still considerable wastage. The Mechanical Engineering and Machine Tool Requirements Board, part of Britain's Department of Industry, sponsored a project to link the cutting force of a fluid jet with computerized planning. Suggested and developed by SATRA, the Shoe and Allied Trades Research Association, the process starts with the conversion of a basic pattern shape into digital coordinates. To achieve this, a series of key points round a paper pattern are recorded. These coordinates are then converted into punched tape suitable for computer input. The pattern shape can then be fed into the computer memory banks. This pattern will vary with each shoe size, and a special process has therefore been devised to enable the computer to work out the variations needed. Other shapes can be recalled from the memory bank, and the computer instructed to work out a cutting layout of maximum efficiency within the given dimensions of sheet material. Ideally suited for synthetics, a fluid jet can cut up to 3 times as many layers as a conventional shoe press. A powerful pump raises the fluid to a pressure of 40,000 pounds per square inch, or 290 meganewtons per square meter. Forced through a 1/4 of a millimeter orifice, the jet cuts to the computer planned layout. The jet nozzle moves across the material at speeds of up to 350 millimeters per second, with the fluid jet cutting at Mach 2, twice the speed of sound. Unlike conventional systems, fluid jet cutting does not distort or move the material, and the width of the cut is very fine indeed. Computer controlled to a high degree of accuracy, adjacent patterns can be butted very close together, and wastage is considerably reduced. The potential of the computer-controlled fluid jet system has many applications for other industries. For example, many of the risks involved in cutting asbestos are reduced because there is no dust. The fluid jet can cope with materials of highly different densities and thickness, such as foam rubber, corrugated cardboard, rock wool, even difficult shapes like this piece of unvulcanized rubber. The SATRA project is just one example of the support given by the Department of Industry's 8 Research and Development Requirements Boards to a wide range of industrial projects.